Hi, everybody. Today we're going to finish Chapter 3 talking about torsion, and it's going to be a fairly short lecture, maybe 20 minutes, but we have just basically 3 slides that we're going to talk about. The first is this slide showing the angle of twist in the elastic range. And the important takeaway from this is just that gamma, which is on the axis of the shaft, and phi, which is on the cross section of the shaft, are proportional to each other by the length of the shaft and also by the cross-sectional radius of the shaft. That produces a profile where when we apply a given torque, that the tau, or the shearing stress, is also proportional from 0 to a maximum at the edge of the cross section, and it's a linear proportion. So using a couple of the ideas that we've had so far, we can calculate an angle of twist using the torque, the length, the polar moment of inertia, and the shear modulus. So the length and the polar moment of inertia are both geometric properties of the shaft. G, or shear modulus, is a tabulated value for the particular material, and T, or torque, is the application, the applied torque in dimensions of force times distance. Now, if you have several different torques applied to a shaft, you can use a summation of the angles of twist in each of them, and the sum total will be the angle at the end. So if you found, for example, the angle of twist in shaft B to E, and from E to D, and D to C, and C to A, you could add them as long as you take into account that this will be going one way, these two will be going the other way, and this will be going back the first way. So this represents a twist in the counterclockwise direction, this in the clockwise direction, this in the clockwise direction, and this in the counterclockwise. So in other words, if you consider this to be positive, this would be a negative angle of twist, a negative angle of twist, and again a positive angle of twist. So you add them, you need to take into account the sign as to whether they're twisting counterclockwise or clockwise. The other thing to remember is that phi and gamma are both measured in radians. So if you're given a phi or a gamma in degrees, you need to convert it to radians, knowing that there are pi radians per 180 degrees. So this just represents a simple arithmetic summation of the angle of twist in radians. Now, continuing on with this discussion, one of the principal uses for this information is the transmission of power in order to move a power from, say, a generator or a motor to something else, so a drivetrain, for example. And the factors that are involved in the transmission of power are the torque and also the angular speed of the rotation of the shaft. So when we design, we always select a shaft both in terms of the material that we use and the cross section, or the size, or the shape, which of course for us we're just going to use hollow cylindrical shafts or solid cylindrical shafts. But basically you have to choose the shape and the size and the material that will support not only the torque but the shearing stress. So the basic equation for power transmission is that power, which is measured in units of energy per time, is equal to the torque, which is units of force times distance, times omega. Now, omega is a rotational speed. In other words, it's measured in radians per second. That can be converted to 2 times pi times the frequency, or the number of rotations per time. The best unit for this is, this would be cycles or rotations per second. This would be radians per second. And so if you think about it in being in radians per second, here you get torque, which is in units of, or excuse me, in dimensions of force times distance per second. So a unit of power in the metric system would be, for example, a Newton meter per second, which is a watt. And in the U.S. customary system, it's foot-pounds per second, which is very small. And the common unit of power in the U.S. customary system is horsepower, which is 550 foot-pounds per second. That was actually a unit that was developed by tractor salesmen when they were explaining to farmers how many horses could be replaced using a tractor. So 550 foot-pounds per second is actually the approximate pulling power of a draw horse. So it's kind of an interesting unit, but it's also very indicative of the U.S. customary system in that it arose by custom, and we're still stuck with it today. Now, another fact is that 1 horsepower is an equivalent of about 745.7 watts of power. So one thing that's important to remember, omega is in radians per second, frequency is in rotations or cycles per second, revolutions per second, and so 2 pi times revolutions is radians. So there's the equivalence of that equation. Now, here we have, this is just a way of talking about a cross-section so that we don't exceed maximum allowable shearing stress. And so we can relate those equations to each other. And using this equation for tau max and this equation for torque, you can equate those two and develop an equation that tells you power in terms of torque or power in terms of shearing stress. So that you can use that more or less in terms of design. Now, the last feature that we're going to talk about today is stress concentrations. Just like before, we had 2 different types of bars. We had a flat bar with a fillet and a flat bar with a hole, and we talked about stress concentration in those. Here we are going to talk about a stepped shaft. So we have a smaller diameter shaft bonded with a larger diameter shaft and a filleted connector or filleted edge in between. So when we do that, the tau max looks very much like the equation Tc over J, which is the elastic torsion formula, only now we multiply it by a concentration factor K, just like we did for normal stress with the flat bar fillet, flat bar circular hole. So here we have 2 factors. We find little r, which is little r over little d, or the radius of the fillet divided by the diameter of the smaller shaft. And then we find a second factor, the larger diameter, the diameter of the larger part of the shaft divided by the diameter of the smaller part of the shaft. So you find the r over d factor, come up to the appropriate capital D over d factor, and you come over here to find a stress concentration factor. So you can see that as this, as we get a smaller and smaller r over d, in other words, where this little d becomes, well, I won't even talk about what that means exactly, but where this factor r over d becomes smaller and smaller, the stress concentration goes up significantly. So the radius of the fillet is a big deal in terms of that stress concentration factor. So when you find that, you just plug it into this formula, find tau max, and that's the tau that you design for. All right, so that's the end of chapter 3. I have posted the homework for chapter 3 in its completion on our Moodle page. When you finish watching this video and you give the homework your best shot, you can ask me questions next time in class, and we will spend a little bit more time just talking about these ideas, but we're not talking about any other ideas in chapter 3. So we'll finish this and then we'll move forward to chapter 4. Have a great day.